1 did not go so well last period. I am hopeful that it's going to go better. We had some technical difficulties that I hope are not going to happen anymore. So let's put the solutions back in the middle of the table. So where we are right now in the course, and we've had this conversation, Mariah, you're filming, right?
Yes.
Okay. There are a grand total of 4 functions that you need to be comfortable with. So we've got little f, the other functions that are connected to this one. You've got what?
Antiderivative.
You've got the antiderivative, big F, which in my mind always lives up here, right? We've got little f, we've got big F. What else? We've got little f prime, and we've got little f double prime. Okay, so let's get some hands on this. Little f has a point of inflection. What does that mean? What does that mean if little f has a point of inflection? Just David and Noemi. David, what do you know if little f is a POI?
That means that f is shifting from either concave up to concave down.
Okay, so that means that little f has a change in concavity. Great. Okay, David, you're frozen for a little bit. What else do we know? Little f has a point of inflection. What else do we know? Giselle, what do you know?
F changes from increasing to decreasing or decreasing to increasing.
F prime makes a change from increasing to decreasing, or there's a change from decreasing to increasing. True. And F double prime? What's that last thing? What's that last thing, Marvin?
It changes from positive to negative or negative to positive.
I'm sorry, one more time?
F double prime changes from positive to negative or negative to positive.
F double prime changes from positive to negative. All right, let's say that I tell you that F prime is positive. Okay, I'm not worried about anybody getting this copied down. F prime is positive. What do you know for sure? I'll take anything from anybody. F prime is positive. Rambir, what do you know?
F is concave up.
Wait, which F?
The middle f.
Little f is concave up? If F prime is
increasing.
If F prime is positive, little f, the function that you took the derivative of to get there, is increasing. You're frozen. What else do you know? Adriana, what else do you know?
The big F is concave up.
Big F must be concave up, right? We've got those relationships happening all over the place. All right, so here's what I want to present you with, and we're going to play around with this for the next 15 minutes or so. Here's the graph of M. Okay, M, the equation is up here at the top. That's great. M for Mavericks. My friends who are Wizards, if you're watching at home, my apologies. I am not meaning to hate on the Wizards. Okay, but this is the M. What I want you to do is give me the sketch of M prime. A justified sketch. So you're going to have conversations with me in 2 minutes like, I know that M is doing this on this interval, so M prime is doing this on this interval. So take 2 minutes, show me what you can do. I'm looking for the best graphs possible. Use that gold sheet if you need to. You've got the graph of little m, I want the graph of M prime. Sketches. Some people have some good stuff going on here. Let's offer up 3 hints. 3 hints. 3 people give me something that you know. Something you know about the graph of M prime. Daisy, what's something you know about the graph of M prime?
It's going to be increasing from, I know it's going to be positive from -4 to -2.
Why? You're 100% right, but why?
Because if M,
Yep.
graph M of X is positive.
Okay, so wait, little m is positive?
Oh, no. From, it's decreasing.
Wait.
I mean,
Decreasing?
no, it's, it's
Okay.
increasing.
Little m is increasing from -4 to, is everybody okay? Little m is increasing?
Yeah.
Okay, all right, it's the end of the day on a Monday. It's okay. Little m is increasing. So Daisy, what do you know about m prime on that same interval? Little m is increasing, so m prime is?
Positive.
M prime must be positive. So however I'm going to draw it down here, m prime better be positive. Good, that's one person. Somebody else. Something else that you know. Ron Beer.
The derivative of little m should not exist at x equals -2.
Okay, so at x equals -2, what do you know about m?
It's a cusp point.
M has a cusp point. Okay, if m has a cusp point, m prime?
Does not exist.
M prime does not exist. One other person. At that point, one other person. One other thing you know. You see the graph of m, something you know for sure about m prime. Go for it.
There's on M there's a point of inflection, so it has to be increased. Yeah.
M has a point of inflection. How do you know that?
Because it's increasing and then it decreases.
Okay, but hold on. If m goes from increasing to decreasing, that doesn't mean that m has a point of inflection. That would mean that the function that you took the derivative of to get here is a point of inflection. Eunice, one more thing. Okay, from -2 to 0, m is decreasing. So m prime is? M prime must be negative on that same interval. So I'm going to go down to m prime, and what I'm looking for in your graph is, do you have all the right things? Is m prime negative where it's supposed to be negative, positive where it's supposed to be positive, not defined where it's not supposed to be not defined? Now there's one more thing that's really special about the graph of m, something that I picked it this way for a reason. Little m is made up of line segments, meaning you know what the slope is. You guys should be able to tell me exactly what the slope is from -4 to -2. What is that slope? Is it 2? If that's -4 and that's -2, it does look to me like the slope is 2. So from -4 to -2, I'm going to graph a horizontal line at y equals 2. I'm not going to be defined at -4. I'm not going to be defined at -2 because of the cusp point. Okay, from -2 to 0, horizontal. From 0 to 2, horizontal at 2. From 2 to 4, horizontal at -2. That's the graph of m prime. That would be the perfect graph for m prime. Whatever part of it you're missing, please fix it. I would expect that at this point in our lives, coming up with the graph of m prime, not too terribly bad. Is everybody okay with m prime? All right, now I want to rock your worlds a little bit. I want to sketch the antiderivative, because this is where we need some practice. Okay, so what I want to do is this. For the next 2 minutes, I'm just going to talk, and I don't even want you to worry about writing anything down. Just take it in. I'm going to see if I can do a little fancy paper folding here. And I want to change the instructions just a little bit. I don't want the full antiderivative. I just want the antiderivative from 0 to 4. And when it comes to these antiderivative problems, I'm always going to have to give you 1 point on the curve. And if you read this problem carefully, what's that point? Read this problem. There's 1 point that you know for sure.
X equals 0, y equals 0. So
It says that big M of 0 is equal to 0, right? So that means that my graph of big M passes through the origin. Here's the point 0, 0. And the fancy word for this is my initial condition. This is my starting point. I know that no matter what, my graph of M must pass through that point. Okay? So here comes just some time. I want you to just listen for a little bit. What I'm going to do is I'm going to look at the graph of little m. I'm going to look at it in sections. I'm going to look at it on this first section from 0 until, what is this 1? The numbers are really small, I'm sorry. From 0 to 1. There are 2 things that I know for sure about the graph of little m. I know that m is negative and m is increasing. Well, if I think about it, little m is negative and increasing. I'm trying to come up with a sketch for big M. big M is the antiderivative. If little m is negative, then big M must be decreasing. And if little m is increasing, then it must be true that big M is concave up. So on this interval where little m is negative and increasing, the graph of big M must do two things at the same time. It must be decreasing and at the same time concave up. Can you guys show me concave up? Show me decreasing and concave up. Decreasing and concave up. We kind of have to look. If I could cut my thumb off for you guys, I would do it, right? So decreasing and concave up must look like that half of the parabola. So I'm going to go down on my graph here, and on this interval from 0 to 1, I'm going to draw decreasing and concave up for that interval. Stop, take down whatever notes you need. Little m was negative and increasing, so big M is decreasing and concave up at the same time. What are the questions that are out there? Daisy.
I have a question. So you did it to like -3, 1 for the coordinate. Like, does the y value matter?
Oh, thank you for asking that question. At this point in the course, we have no idea what the y value is going to be. What I do know is I'm going to start at my initial condition, and because m is negative and increasing, big M is decreasing and concave up, and I'm going to draw that. Where it actually stops in terms of the y value is not important. Other questions? From here.
How did you label that as your segment? How did you pick that?
How did I pick that segment? Great question. So I picked this segment because I knew that on this segment, the sign of little m was the same. The sign, the SIGN. It was always negative on this interval, and it was also increasing. And so I was able to make the connection and say if little m is negative, big M is decreasing. And if little m is increasing, then big M is concave up. Everybody okay? So what's the next interval to look at? We're going to look from 1 to 2. So let's partition that interval. Here's 1 to 2. From 1 to 2, there are two things that are true about little m. Little m is positive and m is increasing. So tell somebody near you, what does that mean about big M? If little m is positive and increasing, what's true about big M? I heard it from a lot of folks. If little m is positive, that means that big M is increasing. And if little m is increasing, then big M is concave up. So I need increasing concave up. Increasing concave up looks like that, right? So on this next interval, draw increasing concave up. Do the next interval. And then the next interval. Because on that first interval from 0 to 1, the little m is negative. Which is why. But that's why I'm breaking it in the way that I am. Okay, I know the sign and I know the increasing decreasing behavior is the same on this. Okay? So Abraham, what's your next interval? From 2 to 3. And from 2 to 3, what do you know about little m?
Shouldn't we be in oh, we're doing the numbers greater than 0.
M is positive and M is decreasing. Okay, so you're off the hook for a little bit. Mariah, what do you know about big M on this same interval then?
Positive.
Little m is positive and little m is decreasing. So big M must be increasing and not negative. Right, what would you take the derivative of for the derivative to be decreasing? It would have to be concave down. So I need increasing concave down, which ought to look something like that. So on this next interval from 2 to 3, I'm going to draw increasing concave down. Jennifer, on this last interval, what do you know about little m?
Decreasing.
Little m is decreasing, and what about the sign? Oh. Yes, negative. That's what I was unfortunately giving away for free. So little m is negative and little m is decreasing, so think about big M. Big M must be, if little m is negative, then big M, the antiderivative, must be, if little m is negative, then the antiderivative must be decreasing. And if little m is decreasing, big M must be concave down. So I'm going to draw decreasing, concave down. It's going to look something like that. And it looks like for most folks, that's what your graph looks like. And you can continue on the other intervals if you want to, but here's the last thing I want to make sure we label clearly out when you graph the antiderivative. Relative extrema and points of inflection. So add those to the graph. I said relative extrema, but what did I really just say? Relative max and relative min. So tell me where the relative max and the relative min occur, and get me your points of inflection.
On big M.
On big M. All of this is for big M. All right, Kimberly, where do you have relative extremity? At x equals 1, so I want to see that on the graph. Relative min at x equals 1. Where else do you have a relative extrema? A relative minimum? Maximum. Okay, and anybody have a point of inflection? Where's that point of inflection? Anthony, where's that point of inflection? Point of inflection at x equals 2. Okay, and I especially want you to label that when it comes to the antiderivative, because honestly, it's hard to tell that you have a point of inflection. I'm curious, how many of you guys looking at the graph of little m knew that big M had to have a point of inflection? 1, 2, 3. Look at the graph of little m. Why does big M have a point of inflection, Jasmine? What?
I don't know.
Oh, you did? I thought you raised your hand for that. You did know.
No, I'm just looking at, I don't know.
Okay, that's all right. So let's look at little m. Daisy, how can you look at little m and know that big M has a point of inflection?
Is it because it goes from increasing to decreasing?
I'm going to forgive you on the word get there. What happens with little m?
Little m, it increases, then it decreases.
Little m changed from increasing to decreasing at x equals 2, which means that big M changes from concave up to concave down at x equals 2. Okay, next question. Look at the graph of little m. Where is the relative minimum for big M going to be? Look at the graph of little m. Where would big M have the relative min? You know where the graph of big M has the relative min. You know. You know. Christian, where is big M going to have a relative min?
X equals 1.
At x equals 1 because?
The graph of them changes from
The graph of little m changed from negative to positive, so big M has to change from decreasing to increasing. I want all of this to just fit together nicely in your brain. I know that there's a lot going on here, and that's why we're going to need more practice. Anthony, are you okay? We're good? All right, so let's set that aside. We are done. That should go in your green folder with the rest of your journal entries, please. The rest of the class period, we are going to the land of physics. Woo! I love it. I am so excited. This is my second at-bat for the day with this. It is going to go so much better. You must have your calculator. Must have your calculator with you. It needs to be fully charged.
It's blinking.
And
My battery on blue.
who drives the laptop? Oh, Martyr, do you still want to drive the laptop? That looks like the no face. Anybody wanting to try driving the laptop?
I wouldn't trust.
Edgar, am I going to regret this?
Yes.
Yeah,
No.
anyway.
No, I have faith in you. You are going to do this the right way.
Yeah.
All right, pull back.
Cute.
Naomi's like, oh, thank God. All right. Okay, while I get Edgar set up, please read this problem and attack it like you would if it was like a unit test or something. All right, the important thing for you to know is that you are just putting
It was like, I don't know, it's like,
use the mouse, right? It works exactly like your calculator does, but you're going to have to drive it. Okay? Also, please over here in the okay? Don't go rogue, Anthony.
like he brought it up.
Control the situation. All right. All right. Mariah, can you read the introduction to the problem?
I can.
Thank you.
There's somebody, Victoria and Nathan, need to attend a fundraising event for the Maverick Nation.
Keep going, keep
Rather
going.
than taking their own cars, they have decided to borrow Mr. B's vehicle for the afternoon. A very bad idea which should not be attempted, ever.
Thank you.
Their velocity as they travel along I-10 can be modeled by the function v of t equals 10 natural log squared of t sine of t for 0 is less than or equal to t is less than or equal to 7.
Okay, so these three young punks from Calculus BC have decided to steal my car. They are driving my car, and we've got a function that models what?
Their
V of t, which is their
velocity on I-10.
velocity on I-10. The units for velocity in this problem? See, some of you are just like, oh, it's meters per second, because that's what we always do in
Meters
physics.
per meter.
No, read the problem. Miles per hour. Okay, here's what I want you to do. I want you to get this graphed on your calculator, and then get it graphed on the paper. Label it all the things that you know you're supposed to do while Martyr gets himself situated here.
Edgar.
Edgar, sorry. I'm so used to Martyr.
It's Edgar.
No, wait.
Escape. Yep, just hit escape. Hit it again. Okay, hit the home button. Okay. You're going to take me over to the graph. So that's B. And graph that function. Now I realize you all know we do not graph in terms of t. You're going to graph in terms of x. Jasmine, please remind me that you are the only one today that has a TI-84 and I need to reach out. So get a good graph. Now, if you read the problem carefully, there's a domain restriction on this problem, isn't there?
Yes.
From 0 to 7. My advice for you, my strong advice is when they give you a domain restriction, use that domain restriction for your window. Because you can only look at the velocity from 0 to 7. Okay, so 10 e to the square root of x, good, times what sine of x? Okay.
I think I got it.
Sine of x, hit enter. Okay, good, I like it, but that's not a good window. Fix the window for me, Edgar. What are we gonna do? If you've already got a good graph, let's get it on your paper so we can mark this thing up.
Wow. Put on 7.5.
Edgar, for your X-min and X-max, because there's a domain restriction, we're just going to go from 0 to 7. Did anybody find a good Y-min, Y-max?
I put in 50 and the graph is still like out.
20 and negative 7. Christian, you've got a really good window. What are you using? Okay,
Yeah,
try negative 100 to
100.
100. Okay. I want you guys to get a little bit of practice with the calculator skills. We're not going to get as much into the calculus and the physics today as I might like. Get a good graph. Give me a quick thumbs up if your graph matches this one. Or at least it's close enough. Now here's the other thing that I think is a really good idea for my college-bound students. Label your axes. What am I measuring on the x-axis? I'm measuring time.
For you guys.
And I'm measuring it in units. So I'm going to put that on there. This is time in hours. And on the y-axis, this is v of t, which is really velocity, and I'm measuring in miles per hour. Okay, great. We've got a good graph. All right, Jose, what's the first thing we're supposed to do?
We're gonna find out where it's increasing.
Where is the velocity increasing? David, how are you, with the graph of velocity in front of you, how are you going to figure out where the velocity graph is increasing?
Use the, increasing?
Increasing.
So, first,
Don't overthink it. This is the velocity graph already. Where's the velocity graph increasing?
from 0 to the maximum.
Oh, I love it. Everybody okay? From 0 to the max, we're increasing. Where else? Marvin, where else?
From the min to anything to the right of it.
From the min to the end, right? So we need to find those points. These are important points. Go find them. Right? For most of us, it's going to be menu, analyze graph. Jasmine, for you, you got it. Okay, and there's a couple of calculator tricks that I want to show you guys as we're doing this. Have we had the conversation already that we are only ever going to be in radian mode?
Yes.
And that's why there's the sign up on the door?
Yes.
Okay, good. Also, your answers have to be accurate to at least 3 decimal places all the time. All the time. So you want to be in like fix 3 or better. All right, so according to my friend here, we've got a maximum at 1.9173. We've got a minimum at 4.9338. Are we okay? Okay, so where's the velocity function increasing? From 0 to, what is that, 1.9173? Okay, I'm going to use brackets, and then from 9338?
3. Yeah, 3.
Okay, definitely. So you are not getting enough decimals, so change your settings. Okay, so I'm a little bit lazy sometimes, but this is a totally legit kind of lazy. I'm not going to write this. Instead, I'm going to write it this way. I'm going to say from 0 to A and from B to 7. Which is okay as long as you tell me what A stands for and what B stands for. So on the side, just write, okay, A means, what was this 1.9173? And B is going to be 4.9338. What's going to happen if you do that? It's going to make the process a little bit faster for you. You're not going to have to worry about writing these decimals all of the time, but you have to make sure you give it to me at least once. Is everybody okay?
Yes.
All right. Good. Part C. Evaluate V of 2 and dV dt at t equals 2. What am I really asking for with that next one? The first one is what is the value of the velocity at 2, and the second one is what's the derivative? So first get me the number answers, then give me like sentence explanations. Are you okay with how to find this on the calculator? That looks like the no face. That's all right. Anybody that needs a little bit of calculator support? All right. Part C, V of 2. Where are my calculator, folks? What are the options here? I can think of 2 ways to find V of 2. 2 very different ways. Anthony, what's one way? Okay, first we're going to have to go menu. Menu, and then you're going to want to do trace. You can do menu, trace, graph trace, and then 2. Just type 2. And now hit enter. Do we see it somewhere? What's that? 37.4017?
Yeah.
Is everybody getting that number?
Yes.
Did everybody get it that way, or did anybody do it a different way?
I did.
Daisy, what did you do?
Well, what I think I put variable.
You did variable?
Yeah, the bar thing.
I just went to the
I put a new document, I just put that in and I put it.
Oh, I understand what you did.
did
I
the
understand what you
basic
did. Okay, another way. Hit the little calculator.
Oh, let me show you guys.
And if your function is already in there, and we called it what, F1?
Yes.
Then you're going to type, and Edgar, I want you to type it F1. So F1. It shows up in bold, so it's a function. Open parentheses, 2, close parentheses, enter. So the 37.4017. Either way, totally fine. All right, Edgar, let's go back. Let's go find that derivative. Derivative, you got a couple of ways. What are those options? How are we going to find the derivative? Oh, it's been a while. Those skills are dying on the vine. Nora, how are we going to find the derivative?
You go to tab.
Oh, I know what you're doing. You're going to like sketch the derivative. You're going to come up with another derivative function. I want to find the derivative at one point. Do you remember? What do you do?
You go to the dictionary.
Okay, that's going to wind up doing the same thing. So here's what's happening. I want to find the derivative at one point. I don't want to generate the graph. The steps, hit menu. And then analyze graph. Anybody see anything helpful there? dy over dx. This is how you find the derivative at a point. Math 9. So it's going to ask for a point, but we want it at a really specific point, Edgar. So just type 2. 2. Enter. Okay, now the graph is getting kind of busy. We got a lot of stuff happening, so grab it and drag it. So it should be that dv dt at t equals 2 is this negative 3.8937. Give me a quick thumbs up if you're actually getting negative 3.8937. I only see 3 people. Okay, we're good? All right, I want answers. I want full sentence explanations on both of these. What do they actually mean in the context here? Let me come on over here. Yep. Okay, did you hit menu?
On the graph or?
Yeah, on the graph. New settings. Okay. And you want to be fixed 3 or more. From here. Default. There you go. Okay. All right, V of 2 is approximately 37.4017. The correct explanation at t equals 2 hours. The velocity is 37.4017 miles per hour. That would be the explanation that I would hope everybody is okay with. Right? That's not a calculus thing. That's just interpret the graph. Who's feeling good about dv dt at t equals 2? One person only. Jasmine, get me started. So what's the sentence that you would write here?
The derivative.
Huh? Okay, I think we're having a communication breakdown because I keep asking who's feeling really comfortable with it, and you keep raising your hand, and then I call on you, and you're like, I don't know.
Did I really raise my hand?
Yes, twice now. I'm not picking on you, but twice. I've been like, who's got it? And you're like, I got it, and then I call, and you're like, it's all right. This is the sentence that we have got to get right, and it starts something like this. At t equals 2 hours. And now I'll stop. At t equals 2 hours. What is it? What happens? At t equals 2 hours, what's going on? Daisy, what do you want to do?
Is it the velocity is decreasing?
Okay, I'm going to freeze you there. The velocity, because that's what the dependent variable is. The velocity is, Jose, what's happening? The velocity is why decreasing?
Because it is negative.
Okay, because that derivative came out to be negative. At t equals 2 hours, the velocity is decreasing. What comes next? What comes next? Abraham.
I was saying that at a rate of 3.89.
At a rate of, I heard you say 3.8937. I'm going to freeze you out. We need to land the plane here. Edgar, land the plane for me.
Miles per hour.
Miles per hour. Everybody's good with miles per hour?
No.
Know what you mean?
Should it be miles per hour?
Miles per hour per hour.
Or
What I love about this notation is the units are right here. What are we measuring velocity in?
Miles per hour.
Miles
What,
per hour.
we're measuring velocity in miles per hour. What are we measuring time in?
Hours.
Hours. So it's miles per hour per hour. Somebody else, I heard you say miles per hour
Square.
squared. These are the explanations that I care greatly about. Adriana, you okay? Happy Monday. I know. I know. All right. There is another thing, though, that I want you to know, that I want to call some extra attention to here. You just took the derivative of velocity, and you got something that is being measured in miles per hour squared. There is one thing in the world of physics, and only one thing in the world of physics, that you would ever measure in miles per hour squared. What's it going to be?
acceleration.
One more time.
Acceleration.
Acceleration. So we found acceleration by finding the derivative of velocity. The calculus connection here is if you have a velocity graph, and you probably already know this from last year in physics, right? When you have a velocity graph and you find the slope, what are you finding? You're finding acceleration. When we find the derivative of a velocity, you get acceleration. I hope that's not a surprise, because a derivative is slope of a tangent line. Okay? All right, so let's beef up the skills a little bit here. We're going to jump past the place where I fell apart with the other class, because I don't want that to happen again. Okay, part E. You with your partner, show me what you can do. On what interval will the velocity be negative and the acceleration positive? So when I say velocity is negative and acceleration positive,
Or is it when it's decreasing?
so where's velocity?
Velocity is being negative. Acceleration is slow.
And what about acceleration positive?
That feel like
This is just.
So let's pull this down.
Why?
Yeah, right?
There you go.
Why are you gonna be crying? So that's essentially what acceleration is.
All right. If I can pull everybody back together. So based on the conversations that I just was listening in on, Everybody seems pretty comfortable with this whole like velocity negative, you know where to look, right? But acceleration positive. What does that mean? Acceleration is positive.
I'm actually reading that.
Are you sure? Because I have witnesses. Acceleration is positive. What do you know?
Isn't that the same as saying the derivative of v of t?
Right? Acceleration is the derivative of v of t. So if acceleration is positive, what do you know about velocity?
It's increasing.
Velocity is increasing. Bravo. So I just need to know where is velocity negative and
Where is acceleration
and I need velocity negative and increasing. You've got the graph in front of you. Go get me where the velocity is negative and increasing. Be careful, it's not from B to 7. It's not from B to 7. Noemi, do you know why it's not from B to 7? Why? Right. So Edgar, what's the work that you're doing back there with the calculator? You found the 0. Right, because what I really need to figure out is from this minimum over to that root. David, were you able to find the root? Oh, no calculator back there.
I mean, mine are off though. I have 3 decimals.
Okay, I can deal with the 3 decimals.
It's 6.283.
Okay,
6.283.
so that sounds like another thing that I want to define. I'm going to say it's 6.283,
Yeah.
and I'm just going to say from B to C.
It's not bracket. No bracket.
Because it says negative at C, it's a root. Okay. So it looks like most folks have got this figured out. We're going from B, which is this 4 point, hold on, I'll flip it together. B is this 4.9338 to the root. And because I want to use my calculator skills as much as possible, I'm just going to add C onto that list of things that I've already found. So C is 6.283. All right. Yes, ma'am.
Why don't you use the approximate symbol? Like instead of the, isn't it like right there, the graph is showing it, so why is it the approximate?
No, but that's the problem. The root is not exactly 6.283. If I allowed more decimals to show up, I'd see more decimals, right? So I'm saying that C is approximately 6.283 because I'm not writing those other decimals. Okay? All right, so now's what I want to see if we can do this. Part F. Using the graph of the velocity function, sketch the acceleration function. You probably want to redraw your velocity function here. But what I really want you to focus on is the sketch of the acceleration. Right, acceleration is really just the drift. So Christian, what are some of the things that you know about the acceleration function because you know the velocity graph?
I count the horizontal tangents.
The what?
The horizontal
Tangent lines. So horizontal tangent line here, horizontal tangent line here. What does that tell you about acceleration?
F5 will have roots.
Okay, acceleration has a root. Acceleration has a root. On this first interval, velocity is increasing, so acceleration is going to be positive. And then the velocity is decreasing, so acceleration must be negative. But I have to hit that root, so I'm going to go down for a little while and come back up. Right?
C.
Because you know acceleration is the derivative of velocity, if you just have your FF prime relationships, things should go well. It's not going to be perfect. David?
The orange is the
The orange, thank you for making me a better teacher here. The orange is my acceleration. So A of t is this V prime of t. Okay, last thing. If you can get this done, things will be good. use your calculator to graph the derivative. This is the thing you guys were trying to do before. Right, we've sketched the derivative by hand. Get your calculator to generate the derivative for you. Okay, you cheater.
I'm sorry, I didn't know.
Okay. And if you two didn't know, it's no chance. All right, hold on. Just get me that derivative graph. Oh, yeah. Okay, smartboard. Tab. Templates button. The thing next to the Bible. Get me a thing that looks like a derivative. There.
Oh, wait, what? I wasn't.
Click on that. Click on it again. Click on it like a man. Okay. Derivative with respect to x of your function, f1 of x. f1. Parentheses x. Parentheses. There you go, the parentheses. Yep, x, parentheses. Enter would be good. And that should look awfully close to what you sketched by hand. The things that I'm going to be ruthless about, are you getting roots in the right places? Is your graph positive where it's supposed to be positive, negative where it's supposed to be negative? All the other things are forgivable. Okay? Tomorrow, you all are turning into me the redone homework assignment from this weekend. There's going to be a lot of number line action happening tonight. If you're not using the number line, you're doing it wrong. And those of you that did not do well on the quiz, you are staying with me. We're going to start in about 5 minutes. And